Find the tangent plane to the implicit surface. X cubed y plus 3 sine x squared z is 2e to the power yz. Now that means what's going on? There's a collection of points x, y, z that satisfies this relationship. We just don't know how to write z as a function of x and y, because anytime you try to get z outside of the sign, you trap this z even more and vice versa. So we can't write z as a function of x, y. That's why it's called implicit. But we still can find the tangent plane, and at a specific point, I should have said 1, 2, 0. All right. Well, we have some options. Do we have an answer? I didn't double check my answer, so hopefully one of these is actually the answer. You're making me nervous. A?
I got -1 for C. So I got 6x plus y minus z.
Okay. All right. So I may have made an error. That's all right. Let's find out. So, but it's pretty close to this one. It's A-ish. Maybe we'll say that, A-ish. Is that a word? I don't know. Well, let's do the process. Now, what's the process? There's two ways to do tangent planes. One is when you have an explicit function, z is a function f of x and y, and the other one says, I don't care, just give me anything and I'll get you a tangent plane. We're in that second category. Now, that category says, we have this beautiful idea called gradients. And gradients are perpendicular to level surfaces and level curves. So we're going to recast this as like, hey, let's think of this surface, not just as any surface, but a level surface of some higher dimensional thing. So, the question, are we ready to take gradients yet? And why not? So, the two-part question. Are we ready to take gradients? Or the gradient? No. Why not? Yeah, we have x, y's, and z's on both sides. We need to get everything to one side. Okay, so we'll rewrite this. This is x cubed y plus 3 sine x squared z minus 2e to the power yz equaling 0. It's the same formula, but now all the variables are on one side. And why are we doing this? Well, the goal is to think of this as a function. We'll come up with a name, g of x, y, z. And the great idea, we say, hey, we remember something. We say gradient of g of 1, 2, 0 at our point is the normal. Because if you're going to make a plane, you need two things, a point and a normal. The point is the freebie. It's the normal that you have to work on. Okay, so we have a plan. Take the gradient, evaluate the gradient, then we have a normal, and put it all together. So, we take our gradient. So the gradient of g, as a reminder, that means we're taking the partial derivatives, g sub x, g sub y, g sub z. When we take derivative with respect to x, what happens to the y's and the z's? Treat as constant. So what is derivative of g with respect to x?
It's 3x squared y.
3x squared y. Good.
Plus 6xz cosine the inside.
6xz cosine, leave the inside alone. So they were doing some chain rule there. And that one doesn't have any x's, so we're done with that one. All right, go to the derivative with respect to y. What is that? X to the third, I heard someone say.
Minus 2z e to the yz.
Minus 2z e to the yz. Okay. Now our last one, g sub z.
3x squared cosine the inside.
3x squared. So derivative of sine is cosine, and we're doing our chain rule. All right, anything else?
Minus 2y e to the yz.
Minus 2y e to the yz. Okay, a little crowded there on the page. Well, all right, now we're not done because we have to plug it in. We have to plug in the point. 1, 2, 0. Now the good news is we see parts with z on the outside. Those terms, where z's on the outside, are just automatically going to be 0. So we don't even have to think too hard about those. Some we have to think a little bit hard about. 3 times 1 squared times 2 gives us 6. X cubed becomes 1 cubed, which gives us a 1. Then we have 3 times 1 times cosine of 0. Cosine of 0 is 1, so that's 3. Minus 2 times 2, that's 3 minus 4. And that's e to the 0. It's hard to read, but that does make a minus 1. So you're right. This was secretly a minus sign. We'll pretend these were all minus signs. There we go. Ha ha ha. All right. So we have our normal. Are we done? Well, what does the question ask us to find? It says tangent plane. You know, sometimes you get so excited. I worked so hard. I should be done. But no, you got to make sure you go all the way to the end. Now the good thing is that the normal gives us coefficients. So you get 6x plus 1 times y plus negative 1 times z equals something. And now we're almost done, but we have to answer the question. What's in the box? What's in the box? So finally, to answer that, what do? Plug in the point. So we get 6 times 1 plus 1 times 2 plus negative 1 times 0. Well, that's 6 times 1. I said the right thing, I hope. Which gives us 8. And so now we have our answer. 6x plus y minus z is 8. Okay. All right. Well, other than I forgot my signs, any questions? So you could do this, right? Yes. All right. Well, on to today. And since today's a special day, we'll pull out a quote from Taylor Swift. It's our Taylor Day. And so here's a quote from Taylor Swift. If they don't like you for being yourself, be yourself even more. And I like that. You know, don't try to force yourself to live somebody else's life. Find the life that you need to live. And so, okay, good pieces of advice. Now, why do I call it the Taylor Day? Because we're building up to Taylor polynomials. And that's one of our favorite topics in Calc 2. We spend weeks talking about it. And so what's going on? Well, we have this idea that we have a way to do approximation. And that's to use our linear approximation, which are the tangent planes. So our function is the function at AB plus f sub x AB times x minus a plus f sub y AB times y minus b. And we pointed this out before, and I'll point it out again. That is on the formula sheet. So the idea of the linear approximation is built in to our formula sheet. But you might say, well, but can we do better? And that's where Taylor polynomials come into play and say, well, let's use more information. What information are we using to make our tangent plane? Well, you look at the pieces that go into it, the value of the function and the first partial derivatives, f sub x and f sub y. So the idea of Taylor polynomial says, hey, if we use more information, we can do a better job of approximating the function, and so we should get a better approximation. And what do you do? Well, you say you have your f of ab, and here this is your zeroth derivatives. You say, I want to make sure I match the value of the function. That says I'm matching the zeroth derivative. And then you have your f sub x ab times x minus a, f sub y of ab, y minus b. And this says, hey, let's match the first derivative. And you pause and you say, well, if I stopped here, that looks familiar. What does that look like? It's what we have up here. So we've been doing Taylor polynomials the whole time. As soon as we start doing linear approximation, that's just a Taylor polynomial. But now, why stop? We can go and say, let's look at second derivatives. So the goal here is you have some terms, f sub xx, so second derivative, both with respect to x at the point a, b, divide by 2x minus a squared. F sub xy, we call this the mixed partial derivative, ab, x minus a, y minus b, fyy at ab, divided by 2, y minus b squared. And this is just making sure, hey, we want the second derivatives also to be matching. So essentially, you're building up a polynomial that up to some point matches in terms of derivatives. So it's matching the behavior. And turns out, the more you match, the better the approximation. Okay, so let's just quickly remind ourselves, linear estimation. And on a side note, if you ever hear the word linear, you should really think flat. So we're trying to approximate something by a flat thing. Tangent planes are the best planes. So among all the planes, among all the flat things that I could use to say what's happening to my function near the point, the plane that does the best job of telling you is the tangent plane. You say, all right, well, good. Now, near is doing a lot of heavy lifting here, because the further away you go, the bigger the error gets. But that's why we only use our estimates for points nearby. Well, we've already mentioned our linear estimators are tangent plane. So let's try this out. Here we have a function, f of xy is 2x cubed plus xy minus y cubed. And we're asked to approximate f of 2.03, 0.98. Now, I know you're thinking to yourself, do we really need to approximate? Don't we have a calculator? Can we just get an exact number, or at least one with a lot of digits very quickly? Well, okay, with this one, probably yes. But what if you were stuck on a desert island and we're passing the time? Like, well, I only have coconut technology available to me. I don't have much. But I really want to know this computation. Well, okay, maybe it's not the worst thing then. So, what do we do? Well, what we do is we say, let's make our tangent plane. So we're going to need some information. We have our function. We'll need to have our partial derivatives, because we're going to build our tangent plane. We have f sub x and f sub y. So f sub x, what's the derivative of the function with respect to x? 6x squared plus y. F sub y, what's the derivative of the function with respect to y? X, 3y squared. Okay, so x minus 3y squared. Good. So we're building up here our approximator, our estimator. So the reason we did that is we say, well, we need information about not just the function, but about the partial derivatives. But we don't want those numbers, we don't want those functions, we want specific numbers. So the next part to do is to evaluate each of these. Now, notice I don't want to plug them in 2.03 and 0.98. So we started thinking, okay, is there something close to 2.03, 0.98 that would be nice to work with? 2 and 1, right? So we probably should have made a comment at the very beginning. We say, aha, this is near the point 2, 1, and we can also make 2, 1 is nice. In other words, it's easy to work with. So the point of estimation is you say, look, I'm near a point that's easy to evaluate for my function, my derivatives. So I can use that information and then say, what's the plane saying I should guess? Okay, so we plug in f of 2, 1. So x equals 2, y equals 1. 2 times 2 cubed, that's 2 times 8, 16. X times y is 2 times 1, which is 2. Y cubed is 1. 16 plus 2 minus 1 makes 17. F sub x at 2, 1. Okay, 6 times 2 squared, 24. Plus y plus 1 makes 25. And f sub y at 2, 1, well, that's 2, which is x, minus 3 times 1 squared. So that's minus 3. That's negative 1. So at this point, we can put this together and say, near our point 2, 1, and 2.03, 0.98 is near, at least we think it is, f of xy is approximately, and now we put our pieces together. The function at 2, 1, 17, plus the derivative, f sub x at 2, 1, 25, times x minus a. So 2, 1, I just point out that's a comma b, so that's x minus 2. And then you add f sub y, which is negative 1, so that makes it a minus, times y minus b, y minus 1. Now, some advice. Don't expand. Now, I say that because when you're trying to do approximation, those tend to become pieces which are very small, and it's easier to not expand out when you're trying to manipulate the expressions. All right, are we done? No, but we're close. Where are we at? We've built our estimator. And now this estimator is pretty good for all the points around, but we're after a very particular point. So our last thing is to say, well, what happens at that very particular point? So f of 2.03, 0.98 is approximately 17 plus 25, 2.03 subtract 2, minus 0.98 subtract 1. Well, even on our desert island without coconuts, we can do these computations. 2.03 subtract 2, 0.03. 0.98 subtract 1.
Minus 0.02.
Minus 0.02. And 2 wrongs make a right. I mean, no. Minus a minus makes a plus. 25 times 0.03. Think about 25 times 3. 75. Then just make sure you have the decimal in the right place. So what is it? 0.75 and 0.02. And so we end up with our approximation is 17.77. Is the answer 17.77 exactly for the function? No. But it's not bad. I don't know the exact value, but our goal wasn't to get the exact value. Our goal was to approximate. And on a side note, identifying these problems tend to be pretty straightforward. Look for words like approximate or estimate. That gives it away. All right, any questions on this problem? Well, you might say, can we improve the approximation? And the answer is yes, but not as a plane. So we start channeling our single variable calculus, put on our Calc 2 hats. We said, well, we can think of ways to do approximations to y equals f of x at x equals a. And the one thing we can do is just say, well, if I plug a into my function, I know what my function is at a. So if I'm close to a, I should be in that ballpark. So I could say f of x is f of a plus some error. And that error tends to be fairly large because it's not using a lot of information. And then in our Calc 1, we said, hey, we could do better. F of x is f of a plus f prime of a times x minus a. Do you recognize this expression, f of a plus f prime of a times x minus a? Tangent line. It's a tangent line, but of course it's not exact. There's error, but the error has gone down. You're using more information. You say, all right, well, let's keep going. We could say, hey, our function, I matched the value of the function, that's f of a. This part here, why do we write it as f prime of a times x minus a? It's so that you match the first derivative. So there's this extra piece that we're going to add on, f double prime of a over 2, x minus a squared. And now, my claim, the error has shrunk even more. And the basic idea is as we use polynomials which match more derivatives, we're doing a better job of matching the function. The better we match the function, the error goes down. Now, one thing that might be confusing, if you haven't seen this 20 times, why is there a 2 there? What is the purpose of the 2?
So now I'm dividing by the number. And I just know it was like the next one should be divided by 3, and then it should be...
Well, it's not quite divided by 3, but I like your spirit. You should say the next one should be divided not by 3, but by 3! Yes? I'm sure that's what you meant. Because secretly, this isn't a 2. This is a 2! 2 factorial. Yes. Now, but why is it here? Well, let's just think about what happens. So this is a polynomial. What happens to this after I take one derivative? Well, if you take a derivative of a constant, it's gone. If you take a derivative of f prime of a times x minus a, it's f prime of a. Now here, f double prime of a over 2, I'll just write that down. That's the constant derivative of x minus a squared, 2 times x minus a, the first power. So now the 2's cancel. So this, I'm just taking the derivative of the first part here. Notice what happens when you plug in x equals a. You get f prime of a. So that's what we mean by saying the derivative matches. Now, do it again. The derivative of f prime of a, 0. F double prime of a times the derivative of x minus a, well, that becomes f double prime of a. So why was there a 2 here, or really a 2 factorial? Was so that as you took derivatives, your exponent came down, so that at the end, you only had the f double prime of a. So you're planning ahead to get cancellation. That's what the 2 is doing for you. So this is single variable. Now you're thinking, well, okay, but what about multivariable? Same principle. So the goal here is we're making a polynomial. We're going to match small partial derivatives. And as we do that, we make a good estimator. We'll oftentimes refer to Taylor polynomials by saying a second order a first order. I think on the quiz they have you do a third order. The order is how many derivatives are you trying to match. So the higher the order, the more you have to put in, the more you're matching. The trade-off is the better the approximation. So it works the same. You have the first part, that matches your 0th order derivative, or in other words, it matches the function. Then you have the next two pieces which match the first order derivatives. And if you just were to stop there, that's your tangent plane. But then you say, okay, I have to match the second order derivatives. Now technically there's 4 of them, but we take advantage of the fact that we work with nice functions, which means fxy versus fyx are the same. So there's this nice symmetry that comes in. So we can reduce it down to 3. So you have your second derivative twice with respect to x, divide by 2, x minus a squared. The mixed partial derivative with respect to x and with respect to y at ab, x minus a, y minus b. Fyy at ab divided by 2, y minus b squared. A couple of things to note. As you look at these subscripts, like here you see an xx, that tells you the piece you're multiplying by looks like x squared. In xy, you have an x piece and a y piece. A yy looks like a y piece squared. So you can match them up to the right pieces. Why do we have a 2 with the xxx and the yy terms? Because as you take derivatives, you're going to bring the 2 down, so you need to cancel. Why is there not a 2 in the xy term? They're 2 separate ones, right? It's really like to the 1 and to the 1. So you take a derivative here, you bring a 1 down. You take a derivative here, you bring a 1 down. You're like, okay, I don't have to worry about the 1s. Secretly, you could say, there was really a 1 times a 1. But we don't usually write it. All right, that's the idea. That's the main theory for today. We still have to do a few examples. We have time to do some examples. We have time to do at least one example. Any questions? Yes?
So I thought there was an f subscript yx as well. Why isn't that accounted for?
Well, that's because f sub xy is the same as f sub yx for nice functions. And we're going to assume that we work with nice functions. So essentially, we're taking advantage of that.
I'd imagine we have to do it twice then.
If you do the xy, you'll get the same thing as if you do the yx for all the functions that we're going to look at. So that's why we can take advantage of it not being there. It's not very easy to make something where the mixed partials don't match, but still exist. You have to work at it.
My question though is I thought you need 2 of them because technically you basically multiply it by 2 and I'm confused why we're not multiplying it.
You don't need 2 of them. Because what's the goal? The goal of Taylor polynomials, it's always the same goal. Make sure your derivatives match. So, if I take the derivative with respect to x, that will become 1. If I take the derivative with respect to y, then this will become 1. And now when I plug in x equals a, y equals b, all these other pieces will have either disappeared or go to 0. Now, you can convince yourself by just carrying out this computation once. But the punchline here is if you take derivative with respect to x once and derivative with respect to y once, literally all the other terms will have disappeared. Like here, there's no y term, so it's derivative with respect to y, that goes to 0. Here there's no x term, derivative with respect to x goes to 0. And so forth and so on. So the only term that's left after you take derivative with respect to x once and derivative with respect to y once is this coefficient. And it's the right number, because I want it to match what I think it should be, which is what's the derivative with respect to x and with respect to y at the point. It works. I promise you it works. I'm not forgetting something. Unlike with the opening problem where I forgot a minus sign, this one I'm not forgetting. At the end of the day, just always ask the question, what's happening with the partial derivatives? And do they match? If the answer is they match, you're good to go. And if they don't match, you don't have a Taylor polynomial. All right, well, find the second order Taylor polynomial for this function at the point 1, 1. Also estimate g of 0.99, comma 1.03. And at the very least, that makes sense because we're at the point 1, 1, and that's near 1, 1. So that's cool. So near 1, 1. All right. Well, what do? We got to take a lot of derivatives because it's second order. So if we have a second order Taylor polynomial, that says we've got to do all of the derivatives up through the second order, and we've got to match all of that. So we say, okay, we brace ourselves. Now, before we jump in too far, we always ask the question, it should always be in the back of our mind, is there anything about this function that we could make it more pleasing to work with? And what is it? Because there is something about this function we could make more pleasing to work with. The log. What can you do with that log? So you can turn multiplication into addition, and you can also bring powers down. So this becomes 3 log x plus 2 log y plus 3x y cubed, and all the rest, 4x minus 2y minus 2. Okay, well, the rest of this problem is not very exciting. No. It's as exciting as it needs to be. Start with the partial derivatives. In the interest of time, we'll go a little bit quicker here. So we're taking the derivative of g with respect to x. So we have 3 over x, because derivative of log x is 1 over x. Derivative of log y is 0. Then we have 3y cubed. And then here, we use the chain rule. It's going to be e to this, and then take the derivative of the upstairs. So we get a 4 coming down. So 4e to the 4x minus 2y minus 2. Similar, we do g sub y, xy. There's no y in the 3 log x. Derivative of 2 log y is 2 over y. Derivative of 3xy cubed, the 3x is a constant. So 3 will come down, making it a 9xy squared. And again, chain rule, we'll bring a minus 2 down. So minus 2 e to the 4x minus 2y minus 2. All right. Are we done with derivatives? No. The fun continues. We're going to have fun. G sub xx. All right, start with g sub x. Taking the derivative of this with respect to x. Does anybody know the derivative of 1 over x off the top of their head? Minus 1 over x squared. Good. Derivative of y cubed with respect to x? 0. And now again, chain rule this. So another 4 comes down, making it 16 e to the 4x minus 2y minus 2. All right. 2 to go. gxy. Maybe we'll skip that one and come back. gyy.
Okay.
So derivative of g sub y with respect to y. So derivative of 2 over y with respect to y, negative 2 over y squared. Derivative of 9xy squared with respect to y, 18xy. And then we have here, we're taking derivative with respect to y, minus 2 comes down again. So plus 4 e to the 4x minus 2y minus 2. Now the only reason I hesitate on g sub xy is I ask myself the question, is there any reason to think, should I take the derivative of g sub x with respect to y, or take the derivative of g sub y that with respect to x. Sometimes one is slightly easier than the other. Do we see any advantage to either one? They're about the same. Now, when I say one is slightly easier, they're equivalent. So I'm not saying you get different answers. I'm just saying that the process getting to your answer might take you more time in one case than it does in another case. So g sub xy. Well, let's take the derivative of g sub x with respect to y. The derivative of 3 over x with respect to y, 0. Derivative of 3y cubed with respect to y, 9y squared. And here, chain rule will be minus 8. E to the 4x minus 2y minus 2. All right, so we've gathered our partial derivatives. What comes next? After you've gotten your partial derivatives all compiled, what do you need to do? You need to evaluate at your point. So g of 1 comma 1, g sub x at 1 comma 1, g sub y at 1 comma 1, g sub xx at 1 comma 1, g sub xy at 1 comma 1, and g sub yy at 1 comma 1. So we get to do this 6 times. Woohoo!
Yeah, that's amazing.
All right, now, good news. What's true about log of 1? 0. So you get 0, 0. Here's a 3. 1's easy to evaluate. Now, what's happening in this exponent? 4 minus 2 minus 2? 0. E to the 0? 1. So g of 1, 1 is 3 plus 1, which makes 4. G sub x at 1, 1, we have 3 plus 3 plus 4, which makes 10. G sub y 1, 1, we get 2 plus 9 minus 2. So that's 9. Gxx is negative 3 plus 16, which makes 13. Well, that's going to make the numbers interesting. Gxy is 9, subtract 8, which gives 1. Gyy, negative 2, plus 18, plus 4, which makes 20. All right. Good. Are we done? No. We probably need another page. Okay. So our approximation, we can write down the generic formula. G of xy is approximately g of 1, 1 plus g sub x at 1, 1 times x minus 1 plus g sub y at 1, 1 times y minus 1. So I'm just writing down the formula for the series. So g sub x at 1, 1 divided by 2 times x minus 1 squared. Gxy 1, 1, x minus 1, y minus 1. And gyy at 1, 1 divided by 2 y minus 1 squared. See, it fits. It's like it was meant to be. Well, we now plug in the numbers. 4, 10, 9, 13, 1, 20. So, that says our real polynomial here is 4 plus 10 times x minus 1 plus 9 times y minus 1 plus 13 halves x minus 1 squared plus x minus 1 times y minus 1 plus 20 halves, which is plus 10, y minus 1 squared. All right, now that is the second order Taylor polynomial. Okay. Cool. Cool.
So all of that is going to be on the exam. Just I'll write all that down.
Well, I mean, you don't have to get the points. There are other things we can do with second order Taylor polynomials to test you on things. So sometimes you'll see this, for example, on the practice quiz. We'll say, hey, I'll give you the second order Taylor polynomial. Now tell me about some of its derivatives. And you say, like, okay, so it's really testing the concepts. And you're like, oh, well, really, the polynomial is storing derivatives. All I have to do is extract it. And then you say, hey, brilliant idea. The Taylor polynomial, the way it works is it matches the derivative. So any derivative I want to match up through whatever order I have, I just take that derivative for the Taylor polynomial, and that has to match what the function is doing. All right, now we're supposed to estimate g of 0.99, 1.03. So g of 0.99, comma 1.03. Maybe we won't do this the whole way, but if all we use is the function, we would say it's 4, right? Which, okay, so great. We match up that far. But what if we use not just the function, but the first derivatives? Well, then we would say it's 4 plus 10 times. Now you take x is 0.99. 0.99 subtract 1 is minus 0.01 plus 9. 1.03 subtract 1 is 0.03. So that is 4 minus 0.1 plus 0.27, which is 4.17. Which means that if you only use the tangent plane, you match that far. But if you went all the way, well, as with what we have here, we still have the first pieces. So the 4 plus 10 times minus 0.01 plus 9 times 0.03. And then we go to the next term, plus 13 halves times minus 0.01 squared plus minus 0.01 times 0.03 plus 10 times 0.03 squared. And if we were really patient, we could work that out. And unfortunately, looking at time, I need to talk about a few other things. I won't. But you would match more. The further you go, the more you're going to match. So once you have it, it's just a matter of evaluation. Now, there's a theory part that's going to play an important role in next time. So don't panic when I put this next page down. All right? Because you might... If you take... Don't panic. Don't panic. If you take your second order Taylor polynomial, you say, hey, what's going on? It's the value of the function. Then there's this like dot product stuff we've talked before. The second order stuff has what we call a quadratic form. And it can correspond to this matrix structure. Now, all of this is going to be swept under the rug. But here's the idea. We're going to talk about points which are interesting, and that is going to come down to when the gradient is 0. When the gradient is 0, what happens to this term here if the gradient is 0? It goes away. So the behavior is driven by the matrix. And it turns out, after you've taken some linear algebra, that this matrix will have two numbers associated with it. They're called eigenvalues, called lambda 1 and lambda 2. And that you can rewrite this as a combination of this number lambda 1 times something squared plus lambda 2 times something squared. Now the nice thing about squares is they're always positive. So the local behavior comes down to saying what happens with these two numbers. If they're both positive, then everything's going up. You look like a bowl that will hold water. If they're both negative, everything is going down. That's a bowl that doesn't hold water. If they have opposite signs, in one direction, you say, I'm going up, so I feel like I'm at the bottom. But in another direction, you're going down, you feel like you're at the top. This mixed signal corresponds with the shape we've called the saddle. If one of them is 0, we don't know. So we can determine the behavior locally if we can figure out what's going on with lambda 1, lambda 2. Now, the good news is we don't even have to know their values. We just need their signs. We saw the signs, and it opened up our eyes when we saw the signs. And there's a nice fact, linear algebra fact. If you have a 2 by 2 matrix, if you take what's called the determinant A times D minus B times C, that's the same thing as multiplying lambda 1 and lambda 2 together. So if this quantity is positive, they have the same sign, which means you look like one of these two bowls. If it's negative, they have opposite sign, which means you look like a saddle. If it's 0, at least one is 0, and all bets are off. So that's the theory for next time. And in our last 2 minutes, I'm just going to put down for reference, because I don't know why they did this. I'm not the one. I'm kind of to blame, but not for this case. They put on your take-home quiz a third order Taylor polynomial for next week. So what do you have to do? Well, you've got to match the first order, right? That's the function. You've got to match, the 0th order. You've got to match first order, tangent plane. You've got to match your second order. And then you say, look, I'm not stopping. You've got to match your third order terms. So if you need a reference for that, this will be scanned in. But the ideas and principles are the same. I'm just going to match all the derivatives. So you'll see like this f(x)(x)(x), there's an x cubed. Why do you need a 1/6? The 3 comes down, the 2 comes down, the 1 comes down. X, x, y, you have an x squared term and a y term. Why do you need the 2? The 2 comes down, a 1 comes down, and a 1 comes down.